You know how AI models went from being sort of clunky chatbots to suddenly writing code and poetry? It feels like this chaotic, unpredictable explosion of progress. But what if I told you it's not random at all? What if it's all following a surprisingly predictable script? Let's get into it, because we're about to uncover the secret recipe. And it's all based on this one groundbreaking paper from OpenAI back in 2020 that basically laid out the master plan for everything we're seeing today.
So here's the big mystery we're trying to solve. Why is every new AI model just astronomically bigger than the last one? It looks like a simple arms race, right? Just throw more money, more power, a bigger hammer at the problem until it works. But is that really all that's going on here?
Turns out the answer is a hard no. It's not just a bigger hammer. What these researchers found is that there's a real science to it, a secret recipe with precise mathematical rules that actually govern how these AI models improve. And the crazy part? Once you know the recipe, you can pretty much predict the future of AI development.
Okay, so first, let's talk about the thing that everybody can see with their own eyes, this massive AI scaling race. The basic idea, the thing we've all kind of noticed, is that for language models, performance just seems to get better and better as you scale up everything at once. In this paper, it didn't just confirm that feeling, it proved it with data spanning 7 orders of magnitude. Performance gets smoothly, predictably better as you add more parameters to the model, feed it more data, and throw more computing power at it. But, and this is absolutely crucial, you have to scale them up together. If any one of these things becomes a bottleneck, the whole party grinds to a halt.
So, if we know the ingredients, what's the actual recipe? This is where it gets really fascinating. The researchers discovered that these performance gains aren't just happening by chance. No, they follow these incredibly predictable mathematical formulas that they called scaling laws. The best way to think about a scaling law is like the ideal gas law from your old high school chemistry class. Seriously, just like that formula connects pressure, volume, and temperature in a predictable way, these AI scaling laws connect model size, dataset size, and compute to a predictable performance level. It literally turns the art of building AI into a predictable science.
All right, so let's break down those 3 key ingredients. The researchers really zeroed in on these as the fundamental control knobs you can turn to tune an AI's performance. First up, you've got model size, which they called N. This is basically the raw capacity of the AI's brain, how many connections it has. But they found this really subtle, critical detail. For the math to work out perfectly, for the predictions to be super clean, you should only count the core, non-embedding parameters. It's a tiny technical detail, but it's the secret sauce that makes the whole recipe work. Ingredient number 2, dataset size, or D. This is the fuel for the fire. It's all the text, we're talking billions, even trillions of words or tokens that the model gets to read and learn from. It's the library of books you give to the brain. The bigger the library, the smarter it can get. And finally, there's compute, C. Think of this as your total budget. It's the raw number of calculations your computers can perform. It's the energy you spend to make that big brain actually sit down and read that entire library of books.
Okay, so we've got our ingredients, we know there's a recipe, but now we get to the most shocking, the most counterintuitive discovery in the entire paper. Honestly, this is the part that changed the game forever.
So let's imagine for a second. You have a massive but fixed compute budget, let's say $1 billion worth of server time. What is the absolute most efficient way to spend it? Do you build a medium-sized model and just train it for a really, really long time? Do you focus on getting the biggest data set possible? What's the best trade-off?
The answer they found was stunning. It was completely backwards from what almost everyone in the field believed. The most efficient strategy, by far, is to pour almost your entire budget into making the model itself bigger, not into training it longer, not into making the dataset 10 times bigger. Just make the model huge. This discovery flipped conventional wisdom completely on its head.
And this quote from the paper just nails it. The best way to do it is to train a very, very large model and then stop the training early, way before it's actually perfected its task. It turns out training a model until it gets an A+ is a massive, inefficient waste of your resources. So what we're looking at is a total paradigm shift. The old way of thinking, train a smaller model until it can't possibly learn anymore, is out. The new, compute-efficient way is to build a much, much larger model and then deliberately pull it out of the oven before it's fully cooked. The priority isn't training time anymore. It's all about raw model size.
So why does this one weird trick matter so much? I mean, why is this such a big deal?
because it gives every AI lab on the planet a clear, strategic roadmap. It's the reason we're seeing this explosion in model size today.
The core reason this works is a concept called sample efficiency. And what it means is that really big models just learn faster. A much larger model can reach the same level of intelligence as a smaller model, but it needs to see way fewer examples and takes way fewer training steps to get there. Its sheer size gives it this incredible head start in the learning race.
The paper even put a number on it. They found this specific mathematical relationship. To keep your training efficient, the amount of data you need grows much more slowly than your model's size. So get this. If you make your model 8 times bigger, you don't need 8 times more data. You only need about 5 times more. This is what makes building these monster-sized models actually possible without needing to, digitize every book ever written.
And let's be super clear. This is not just some academic theory. This is the playbook. This is the business plan. These scaling laws are the reason companies have the confidence to go out and spend billions of dollars on compute power to build models with trillions of parameters they can actually predict with decent accuracy the performance they're going to get for that massive investment.
But, a recipe this perfect and this predictable, it can't last forever, can it? I mean, something's got to give. And the authors themselves, they looked way into the future and found this fascinating little paradox hiding inside their own equations.
So here's the paradox. The recipe for efficient training tells you to prioritize making the model bigger, not the dataset. But if you follow that logic out to some crazy future scale, you can end up with a model that is so enormous that it just memorizes its training data instead of actually learning general rules about the world. So you're stuck. The most efficient way to train the model might also be the way that risks it becoming a brilliant idiot that just parrots back what it's seen.
And that brings us to the ultimate question. These laws have held up beautifully for years, across mind-boggling increases in scale. But nothing in science lasts forever. So what happens when we finally hit a wall? What happens when these clean, predictable rules just start to break down?
Which leaves us with this final thought to chew on. With these scaling laws, have we discovered the map that leads us to the fundamental speed limit of AI itself? Is this as good as it gets? Or are we just looking at the end of the first chapter, right before a completely new kind of science is needed to take the next big leap?